Light absorption starts with a simple idea. Light carries energy, and molecules can only accept that energy in specific amounts. When the amount carried by a photon exactly matches an allowed energy gap inside a molecule, absorption happens. The energy of a photon depends on its wavelength. Short wavelengths, like ultraviolet, carry high energy. Long wavelengths, like infrared, carry lower energy. That relationship is captured by the equation E equals h nu, or equivalently, hc over lambda. You do not need the numbers here. The only thing that matters is the trend. Shorter wavelength means more energy. Molecules are not free to take any amount of energy. Their energy levels are quantized. Think of them as steps, not a ramp. You can stand on one step or the next, but not in between. A molecule absorbs light only if the photon energy matches the gap between two allowed steps. Those steps come from different kinds of motion. Molecules can rotate, they can vibrate, and their electrons can change orbitals. Rotational gaps are small, so they absorb microwaves. Vibrational gaps are larger, so they absorb infrared light. Electronic gaps are larger still, so they absorb ultraviolet or visible light. When you look at a UV visible spectrum, you are mostly seeing electronic transitions. Absorption is not just about matching energies. Light is an oscillating electric field, and molecules contain charges. For absorption to occur, the electric field has to be able to push electron density around in the molecule. This requirement is summarized by what chemists call the transition dipole moment. In plain terms, even if the energy matches, the molecule must be able to redistribute charge during the transition. If it cannot, the absorption will be weak or essentially forbidden. Electronic absorptions are extremely fast, on the order of a femtosecond. Electrons move quickly, but nuclei are heavy and slow. Because of that mismatch in timescales, the nuclei do not have time to move during the electronic jump. This idea is known as the Frank-Condon principle. The transition happens vertically, at essentially fixed nuclear positions. As a result, a single electronic transition usually connects to many vibrational states at once. That is why absorption features are broad bands instead of razor-sharp lines, especially in liquids. Now connect this to molecular structure. In organic molecules, common electronic transitions include pi to pi star and n to pi star. Pi to pi star transitions occur in double bonds and aromatic rings. They are often strong because electron density moves easily across the pi system. N to pi star transitions involve lone pairs, such as in carbonyl groups, and they are usually weaker because the charge motion couples less effectively to light. A very useful way to think about absorption wavelength is the HOMO-LUMO gap. The HOMO is the highest occupied molecular orbital. The LUMO is the lowest unoccupied molecular orbital. Absorption promotes an electron across this gap. A large gap requires high energy light, so absorption stays in the ultraviolet. A smaller gap requires lower energy light, so absorption shifts toward longer wavelengths. Conjugation shrinks that gap. When pi bonds are connected in a conjugated system, electrons are delocalized over a larger region. Delocalization lowers the energy difference between occupied and unoccupied orbitals. As conjugation increases, absorption shifts to longer wavelength. That is why highly conjugated molecules can absorb visible light and appear colored. The part of a molecule directly responsible for absorption is called a chromophore. Groups attached to it can tune the absorption. These are called oxochromes. They often donate or withdraw electron density through resonance, changing both the wavelength and the intensity of absorption. Chemists use this idea deliberately when designing dyes and indicators. In the lab, absorption is measured using the Beer-Lambert law. Absorbance equals epsilon times concentration times path length. The key parameter here is epsilon, the molar absorptivity. It reflects how allowed and how intense a particular transition is. Strongly allowed transitions have large epsilon values. Weak or forbidden transitions have small ones. The environment matters too. Solvents interact with molecules and can stabilize ground and excited states differently. If the excited state is stabilized more, the energy gap decreases and the absorption shifts to longer wavelength. Collisions and varying local environments also broaden absorption bands, especially in condensed phases. Finally, absorption is not the end of the story. It creates an excited state. From there, the molecule can relax by releasing heat, emitting light as fluorescence, crossing into a different spin state, or undergoing chemistry. Absorption is the doorway. Everything interesting happens after the molecule steps through it. So, the full picture is this. Light arrives with a specific energy. Molecules have discrete energy gaps set by their structure. If the energy matches and the transition is allowed, absorption occurs. Nuclear motion spreads that absorption into bands. Structure and environment control where those bands appear and how strong they are. And absorption marks the beginning of excited state behavior, not the conclusion.